basically about the controller for the inverters that can be used, inverters or rectifier sequences that can be used for either fuel cell or electrolyzer. So mostly we will discuss in common how to control those inverter rectifier as in the grid following mode. Okay, over to Professor.
If you remember what we discussed before, that inverter needs for electrolyzer or fuel cell? For fuel cell, right? Because fuel cell produce DC power and then we convert it from DC to AC. But again, I mean, for electrolyzer we need DC input, right? So itself for electrolyzer we don't need inverter directly, but if we have other devices in the system, then we might have inverter in the system. But when here we are talking about grid following or grid forming, we mainly think about only if that hydrogen, then it's a electrolyzer. But when you have got other system, then the electrolyzer would come into the picture. Okay. But here, even if you see that simple diagram, we will understand what's the difference between grid following and grid forming, right? So when we have got a big a grid, and if your grid is strong, then normally the grid following inverter is more than enough, whatever device you're going to connect with the grid will not have any problem. But when you go for the microgrid, mainly off grid mode, or you have the main grid, but the grid is relatively weak grid, then we need actually grid forming inverter. Because you see in the grid following inverter, it just follow reference power whatever you are giving. So always our intention to inject either only real power, or it could be, if you want to control it, it would be both active and reactive power. You don't care about voltage, frequency, when it is connected. But here, and definitely that's operate in the current source mode. It's a current. If you remember that we talk about voltage source inverter and current source inverter, so that's a operate a current source inverter. And when you have current source, definitely you know that there is a in parallel impedance. So that's how we electrically represent the grid following inverter. Grid forming inverter is a voltage source inverter, and here you see that we have got input not only power, but also the voltage and omega, which is frequency, right? Because omega that twice pi f, so so it does have the capability to control voltage, frequency, and later we'll see that it does not need any PLL, because it actually form the grid, so it produce that one. But for GFL we normally use PLL, from by measuring the voltage current from the frequency, and then we use that one for the control purpose. So these are the few things that we're gonna talk about, mainly the role and application of grid tied. Sometime normally called inverter, sometime we call converter as well. What is GFL? What we already talked about types, some application like architecture, advantages, limitations, some scenarios, some real project that is actually happening with grid following, and grid following, we don't need any special project because that's already quite established, but also some project happening with the grid forming, and then finally we'll conclude it. So we already talked about rectifier inverter. I mean, we don't need to repeat it. We already talked about AC, DC, DC, AC and their applications. But here, I mean, although we have like different types of converter, but like core component in the grid, now in the they are the like the core component in the modern grid, because as I said there are so many power electronics devices using. So at some stage probably still I mean it's not that power electronics actually dominating the grid dynamics, but when you have got 70-80%, they actually dominate the dynamics. At that time definitely we need to do the electromagnetic simulation, not electromechanical. So the inverter I mean is operate either in a grid following or grid forming mode. That's also probably we already covered most of them, like yeah, I mean step up, down, that's also we already talked about. For renewables also I mean we need to convert in different phases, that's also we have talked about. And if you have got in the system like the DC fast charging, that also I mean use the rectifier, and if you have high voltage DC, that also need the conversion as well. And then it also use like when UPS, microgrid or vehicle to grid technology. So in all of the cases I mean we have the applications of that inverter converter for grid connection. So as I already mentioned that GFL control makes the inverter to follow the grid voltage and frequency just like a listener. So it's just like a follower or listener, whatever the grid does it will just follow the grid voltage and frequency. It will not providing any commands to the grid to follow the inverter itself. So that's why it's just like a I mean grid are the like a leader, and GFL you can think of that's like a follower. And so here you can see that I mean if you have the grid and if you have the inverter, I mean magnitude could be different, but exactly it gonna follow. So that's like a grid following inverter. And then as I talked that we need PLL to synchronize with the grid voltage. So it tracks like voltage and frequency, and use that for that purpose use that PLL like I mean whatever the reference you are getting from that, it gonna produce that reference, and then from that whatever the current controller we use, from that I mean using that theta it gonna produce the control signal for the inverter. But as I mentioned previously, it's just saying like active and reactive power to the grid based on the grid condition. So if you give like unity power factor, then definitely it's gonna give only active power. But if you have non like unity power factor, then we will give both active and reactive. Although I mean as a honor your preference would be unity power factor, because then you're gonna get maximum benefit. Because still I mean what happened, like if you have a rooftop PV in your home, only you will be paying for your active power that you're gonna sell to the grid. But if you give reactive power, still I mean there is no reactive power market, right? So you're not gonna get any payment. But sometime for the grid condition to stabilize the voltages, you are actually forced to give some reactive power. But when you give reactive power, what happens? You are compromising with your active power, right? So let's say if your capacity is 10 kVA, if it is unity power factor, you can get 10 kilowatt. But if it is 0.9, you will not get 10 kilowatt, because active plus reactive, that's actually get the whatever rated capacity. So you're going to be compromising. So that's why we normally prefer to give only active power, but as I say, sometime you control for both active and reactive as well. So again, I mean, yesterday when you saw that all the control, most of the control we design, is it in ABC frame or in DQ frame? In DQ frame, right? Because DQ is mostly, although I mean our voltage current is sinusoidal, but when you convert it into DQ, it operates like a DC, right? And it's easy to design the control. And again, I mean, I'm not going to talk about now, but you already know that we need to convert from ABC to DQ and then vice versa. So that, and for the conversion also we need that angle theta. So using that one, I mean, we do that conversion, and then whatever control, sometime we have got, as yesterday mentioned, that in many cases you have got outer and inner control loop. Sometime you also have only one loop, but based on that, I mean, then we design control. But here what it says, that when you have got this grid following inverter, the PLL dynamics, that actually plays significant role in your transient and also in your system stability. So you need to consider PLL when you're gonna be dealing with grid following inverter. And the voltage that here you are measuring, if it is get distorted, actually it significantly affect the PLL operation. That sometimes also affect the system stability as well. So again, I mean, there are many PLL also available in the literature, but just the very simple one, it does have problem when you have got distorted voltage. But if you have got pure sine wave, no problem. But if you have got distorted, there are many different types of PLL, but still the PLL has got problem when you have got like distorted voltage. In that case, I mean, it might affect the, as I say, like transient and voltage, I mean, system stability. So here, like the in grid following inverter, so the current control mode actually regulate the inverter output by tracking that reference current, and this reference current again, I mean, come from the reference active and reactive power. So one of them is related to active, another one is related to the reactive. So D axis, which is mostly like active power, and this one is like the reactive power. And then from there, whatever output we are getting, we then convert from DQ to ABC, and then we apply it, I mean, to produce the control output from that pulse width modulation, right? So it actually control the duty cycle and also some angle, sometime angle as well. And by controlling that, I mean, you can control the active and reactive power. So this, I mean, mostly if you classify all the grid following control, then as I said, this is definitely current source control, but you could have either grid feeding or grid supporting, right? So if it is grid feeding, that I already mentioned, like PQ control, it's just feeding the power to the grid. But if you want to support grid, then sometimes people use like the droop control or voltage VSC, I mean, it's like virtual synchronous machine type control as well. So again, I mean, if you grid supporting, then I mean grid is by dynamically responding to the grid. Droop control, that actually probably that is one of the very established control technique that's available for like an inverter. So mainly used to share load using either power frequency or in some cases both power frequency and voltage reactive power droop as well. But again, I mean there are so many droop also available in the literature, and this is current controlled, that's try to emulate like a synchronous generator inertia and damping for frequency support. So PQ control, I mean this is mostly the simple PI control, that's Dr. Animesh talked yesterday, that proportional and integral, and both proportional and integral has got their own function or own control purpose. So one of them will try to reduce the steady state error, right? Another one will try to be messing that overshoot and settling time. So again, I mean how to determine this KPKI, there are so many technique available in the literature, and also it's not that always you have to do it manually, also auto tuned PI control is also available in the market as well, I mean in the literature as well. So depending on the system condition change, it's automatically update I mean this KPI and KI based on the system operating condition. But I mean once you have that the model, state space model with 4 matrices, you can easily do the transfer function, and then by using I mean root locus, and there are so many other way, I mean Ziegler-Nichols, and there are many actually techniques that's available to determine this constant. People also sometimes try to do trial and error, I mean to find out what the base parameter, and then nowadays even like AI and other things also can be utilized to tune the control as well. But this is one of the control that used for like PQ control for the inverter. And if you have a like a droop control, so like frequency and power, I mean the relation is given by a droop. So by changing that I mean droop coefficient, this is for like frequency and this is more like a voltage, then again I mean you have that reference, you have measure from that, you will find whatever like change in that signal that's coming again with the measured power, and that's how you produce the reference frequency for your inner the current control. Again here we are using the same PI that I have shown in the previously. So the only difference here that you are using to droop, I mean for that power sharing purpose. So when you have got multiple device, I mean how they gonna share power, and when they have got like changes in the load or changes in the even like generation, this gonna be automatically changing the droop to change is like output power depending on the voltage, depending on the frequency, and that's how try to improve the dynamic performance as well as I mean system stability. And then this like emulating the synchronous generator like characteristics. So probably all of you know like that I mean well established synchronous generator model. Sometimes they just capture that electromechanical dampings, electromechanical dynamics, but sometimes they also try to include like voltage as well. But here I think this is only that inertia damping, that using that well established swing equation, where you have got like the damping, frequency, and real power. So, by using that equation, you gonna include that one in your control in such a way that by using damping, inertia, everything, it gonna be producing that like input signal at the end to your controller. So, as it does include those parameters, it try to actually mimic the behavior of the like synchronous generator. Now, in terms of like so those some of the control technique that use, but as I say, like there are so many other also available in the market, in the literature, because market, I'm wrong, market mainly actually PI control, but like the literature you will find so many different techniques people have already applied in their designing, but in terms of like commercially available, mostly you will find PI. So, it does like widely utilized in different like renewables. Now, mostly now even in the like the power grid, if you see like mostly all the photovoltaic system and then your wind farm, they actually have this grid following inverters, but some of the battery they have grid forming. I know in Australia none of the photovoltaic system or wind farm they have got grid forming, only some of the battery they have got grid forming. So, so far the commercially one available only for the battery, but I'm not saying that it cannot be done for other devices, it can be done, but so far that's the scenario. So, even like as I said, not all the base has got grid forming. So, if you have grid following, it just manage the charging and discharging while it maintaining the synchronization with the grid. And their main purpose is not like participate in the ancillary market, but mostly like support like the peak shaving. If you have got energy either deficiency or like surplus energy, then charging and discharging. So, that's how they support the grid. So, if you use like the battery, this is one of the way you can use that GFL with your inverter. So, here you are measuring voltage and frequency from your PLL, then you are using your droop, but this one definitely you're going to provide the some control function, otherwise you don't need the droop, you can directly go for your normal control that I mentioned. But if you want to provide control function to the grid, then you can have this, and then at the end you can have your like in the sometime double, sometime could be like only single, that inner control loop, which is mainly actually control through your pulse width modulation, and then provide whatever service you need for the grid. So, here that base definitely provide active reactive power, support to voltage and frequency under grid following control, not like grid forming. Yeah, sometimes you also can contribute like frequency fluctuation, but at the same time it will do the like main function for your peak shaving, load balancing, and storing renewable when you have got additional generation in the system. This is even like another technique, even better function provide better service compared to the previous one, because the previous one only have the droop and then internal current control, but here you can see there is one more control here, which is low voltage right through. So, by including that low voltage right through capability, so low voltage right through, again I mean depending on the system grid core requirement, there is the like that for if you have 0 voltage, how long you need to connect, and then from 0 to at some other voltage. So, that is like different requirement. So, as long as within that voltage range, when you have got that grid fault, so depending on that this LVRT control, it gonna be producing some reference power, which at the end will be adding these two, and then it will like apply as a reference Q axis current to the inner current control loop, and other one is just like real power, which is at the end connected to the related to the frequency as well. So, by if you use this sort of control architecture, so I mean it can actually synchronize and provide active reactive power, as it is using droop control to adjust output power based on the gate frequency or voltage variation. But as I say that during this fall, the system also applied that LVRT logic to maintain the required current and ensure that the whatever either renewable or the battery, it gonna be providing service to the gate without like that tripping. So, it actually include that LVRT capability, and as I say like nowadays many of the grid cord, they demand that if inverter is beyond like certain like capacity, it must have, I think in Australia it's more than like 30. If it is more than 30, then you must have like low voltage right through capability with your inverter. So, this one more like if you have got like hydrogen electrolyzer, or as I say like if you have like other devices, it could be so I mean normally fuel cell, but it could be electrolyzer as well. I mean if you have other devices in the system. So, again I mean the technique would be quite similar, that you will be having that PLL and then that power control, and at the end you will have that output control signal, which is voltage and angle. It gonna be coming your current source control mode, then I mean it will be connected with the grid. So, yeah, so again I mean the control technique is at the end is same, only difference would be like your whatever devices you're gonna use it. So, it's not that any significant difference when you are using like that green hydrogen system instead of like renewables or battery. So, again I mean yeah, I mean only difference would be that whatever the converter inverter technology we mentioned, that gonna be utilized, but overall like the control design framework would be quite similar, but definitely I mean the model would be different. Your at the end I mean the control parameter would be different as well. Now, for using like GFL, I mean the key advantages as like it's quite simple, and as this is massive technology as well, it cost effective because it's easy to implement, and also it's easy to compliance with the grid code as well, because it has been using I mean quite a while. It also need like less computational, less sensing, which reduces the cost and simplify the design. So this is like the summary of whatever the key advances I mentioned, that compliance, cost, maturity of the technology. Yeah, I already mentioned that application, that GFL use your solar inverter, EV charger, wind farm, UPS, and the reason why is used, we already mentioned, like that low cost, plug and play, follows grid without anything extras. Synchronization is also easy, and uses like existing PLL as well, but it does have like limitation when, as I said, like mainly when you have got weak grid. So anyway, probably you know already, right, what is strong grid and what is weak grid. How do we know which grid is strong and which grid is like weak? So mainly from the short circuit ratio. So depending on the short circuit ratio value, or other could be like even fault current capability as well at the point of common coupling. So if you measure the short circuit ratio, I think if it is less than the 3, then we call it weak grid, and if it is more than 3, normally we call it strong grid. And there is a simple equation also you can use, like in like y, how to measure the short circuit ratio. So in certain condition, I already mentioned that GFL fails, mainly in the when it is like isolated microgrid, like here no voltage reference, converter cannot operate, and when you have got weak grid, you have got voltage sag, you have got unstable current, and then in those cases we mentioned that GFL fails, and we have got disturbance, as I said, like the PLL looks to give like the wrong angle, that can give incorrect power, and then your controller will also provide incorrect control signal that can actually deteriorate the system performance and can introduce sometime instability problem as well. I already mentioned that for weak grid you have got low short circuit ratio, voltage sag, distorted or very noisy grid voltage. So that will indicate that weak grid impedance and poor voltage stiffness typically occurs when you have got like the remote location. But the thing is like that in most of the cases you will see most of the renewable energy zone that connect in the remote area, not in the CBD, right? So that also even like make the problem complex, because the weak is already grid, and again we are integrating most of the like large scale when you have got renewables in the weak grid. So that's why we need better control and also like grid forming inverter. Voltage sag that might cause like caused by voltage, sudden load change, and also light impedance. Noisy voltage can be coming from harmonics or when flickers from nearby load. Also sometimes it can come from converter that can distort the voltage as well. So that although there are so many inverter converter, but you see that many of them does not produce pure sine wave. So always converter inverter that actually contribute for the power quality problem. Also the different advanced filter, it can address that problem, but again still there is a possibility that it can distort the voltage, and once you have this problem, as I said, GFL inverter may become unstable, as control assumes like a strong voltage input. But if you have a like poor, then yeah, it can actually become unstable. It cannot support and disturb voltage again when you have got that weak grid. and distorted, as I say, like PLL can fail. So that's also, I think, probably we already talked about what are the root causes of this, like low SAR, distorted waveform, high grid impedance, fast dynamics, voltage sag or voltage, voltage unbalance. That is also one of the problem, in recent areas also. When we are connecting different photovoltaic system in a different phase, because most of them like in a single phase in your home, right, and people connect in different phases, sometimes that also causes voltage unbalanced problem as well. That's I already mentioned, less than 3. That's normally we called it like weak grid. Yeah, so I think all of them probably we already covered. So now I just quickly show one like simulation result, then probably I'm gonna stop. So here you can see just like you have a system where can be connected with the grid. Initially definitely it's grid connected. Then you have got number of devices like PV, wind, you have got load, but also you have got that green hydrogen system as well, like electrolyzer, storage and PM cell. But what happens here for this type of study, that when one of them like in operation, other one actually stop. Is any question or okay? So it's not that both alkaline, electrolyzer and fuel cell operating in the same state. So when one of them operate, another one is actually stop. So that's how in this study done. And therefore, I just mentioned like what like different capacity they are using, like, and then like all the model that I discussed yesterday, by using all those model, and then here how that your electrolyzer and fuel cell will work, that actually given this simple rule based control, like depending on the power coming from PV, power coming from wind turbine, and then the system load, and then because electrolyzer also that this is a load, right. So by combining of two things, and then what are the like your storage, hydrogen storage, because storage always has like minimum and maximum, right, like the battery we have got minimum SOC, maximum SOC. So here also like sometimes people see like 10%, 70%, between that it will decide whether your electrolyzer is on, and as I say, when electrolyzer is on, PMA is automatically blocked. So that's like a switched off. And then in other condition, like your total generation is less than the load, and also if it is P minimum, is that the condition, then your PM fuel cell is switched on, and then electrolyzer is switched off. So this is only that rule based control, that how you gonna operate your fuel cell and your electrolyzer. When you will produce chemical energy, when you will produce electrical energy from chemical, depending on the loading condition, depending on your storage capacity. So by doing that, yeah, again this is the same thing that the single line diagram shows, and then it shows like whatever the condition as mentioned, it actually satisfy exactly the same thing, that you have got the load demand, and then how much power coming from solar, how much power coming from your wind, how much power coming from your grid. Based on that, what time your electrolyzer is actually consuming the input power, or when your fuel cell actually producing the electric power, because in those cases we need to have the energy balance, and depending on that how your that storage tank also having the storage capacity as well. So by doing so, you will be able to understand that the model that you have designed, is it making sense, because at the end as I said that all the generation will be equal to your consumption. So that's the one way to also validate your model, and once these are all right, then you can go for other type of study as well. But this is like your minimum things that you can do. So other things I'll just also quickly show another only here you have got grid following inverter, and this is more like a single machine to infinite bus, but here also there is a load connected. So again this is more like detail that your ABC signal, you are measuring, then you are converting, and then you are doing the power calculation, and then you are designing the control. At the end, after having that control signal output, because at the end you are coming back to the your main system, you have to again go back to DQ to ABC. So that's actually showing the whole total things. If you want to have that voltage in ABC, current in ABC frame, but if you want to do only DQ frame, then you don't need to do all the calculation. So as Dr. Onmesh mentioned yesterday, that once you actually design the control in any form, the first step would be that you just check whether your control design makes sense, and once it makes sense, then probably you can do further simulation to showing that how your control design is performing, either to control voltage or to control frequency, or other things. So here whatever that design I showed, even number of them available in the MATLAB as well. Here also I mentioned all the parameters. So if you want to check it, you can do this. So here the capacity of the converter is 15 kilowatt, and here you can see that, sorry, here actually we have got 10 to the power 4. So it's here 15 at this point. So what actually we are doing here, we are suddenly changing the reference power. So it was initially 15 kilowatt, but you are asking to reduce that power that you're going to get from the inverter 10 kilowatt. So if you want to do that, if you make the changes, how your control signal is performing. So you see, this is the reference, and you can see that it is actually following the reference, both real power and also reactive power. Definitely, depending on the control, sometime it might track within shorter period of time. Sometime you might have some overshoot. You might sometime have also some oscillation, depending on how good your design. But at the end, if it is follow that reference, then you will be sure that your design actually makes sense. So that's the always the test that you should be performing after designing the control. And you see that not only PQ, but also that DQ current reference also it follows, as we are giving like 0 reactive power normally. So, that is why it producing 0, but what I am trying to say that it actually following the reference. So, maybe I will stop it, because the other one more like grid forming. So, I will show you maybe in the next one, but here I just put it because at the end I just shown like the comparison when actually you have like different sort of like inertia level. So, here initially it was like 7 SCR, but later I mean when you change the SCR, that is the problem. As I said, the grid following fails. So, you see that when SCR is less than 3, the problem occurs. So, that this is rate of change of frequency. So, when you have got very low short circuit ratio, your grid following have the problem. But you see the grid forming is still okay, even the short circuit ratio 1. So, we started 7.5, and then like here when it is very low, this problem occur. And as I say, like how you can measure short circuit, you just need the short circuit power of the grid, which is PSC, and then the denominator one is just the capacity of the installed generator. And how you can determine this power? So, if you know that voltage, grid voltage, and also the grid impedance, also I mean this is quite challenging to measure it, but there is a way I mean you can also measure the impedance. So, that is how you can measure the SCR. Always those of you are working like the grid level, it is advised that you measure the grid strength first, so that you will know like the control, everything you are going to be design. Are you designing for strong grid, or you are designing for like weak grid? Because based on that, I mean you should be choosing your control strategy. And as I said, this is not that difficult. This is one way, but also as I said, like fault current contribution, from that also we can do that. But yeah, I mean it's better to do it. And as I said that, I mean once it is weak, then we have to go for the grid forming, which I am going to discuss later. Thanks for your attention.
So, any questions from the audience?
Good morning, sir.
Good morning.
There is one question where you showed one case study, 15 kilowatt grid connected converter. In that grid impedance, what you have selected, that is 4 millihenry and resistance 0.2 ohms. Sir, how did you select these values? Because grid is, we say it is a infinite one.
Yeah,
for testing.
For what we did, like for the simulation purpose, just to show like that if you, because when you have got like different types of grid, definitely that value will be different. But just to check here that if we change considering that one initially, that gives like a strong grid, that SCR value. If we have that impedance, that is actually giving that initial value 7.5. So, that is the reason we picked up that value, and then we change it and show that because what will happen, that like that impedance, that equation we showed, again I will just open it. So, if you see that higher impedance, that means SCR is low, right? So, SCR is low. So, we just picked up that value initially, but as I said that there is a way you can measure the grid impedance, but here we didn't, we just pick up a value that give that particular short circuit ratio.
mentioned that harmonics level could be reduced below 5%, IEEE's acceptable limits. So what is the limit for voltage instability, sir, according to IEEE?
In different country, there are many different requirements. In Australia, for like low voltage grid, we have got I think plus minus 5%. But for India, I'm not sure, but should be close. But in high voltage, sometimes they consider plus minus 10. But for voltage is plus minus 5 for like low voltage distribution grid. And for frequency, some country it would be like plus minus 0.25, some country plus minus 0.5, like 50.5, and lower is 49.5. But in some cases, like 49.75 and 50.25, that's the limit.
I want to give a heads up that I am sharing the slides everyone. So if you see the course plan, the end day we have a 1 hour exam. So I request all of you go through the slides every day. So you will have some handwritten exams here, and you will get a transcript on that once you get maybe some credits for passing the course. Okay. So we'll have a 15 minutes high tea break. It's arranged. Please have it and